Okay, let's answer the question, what is a tangent line? And what does it mean for a line to be tangent to a circle? And what is the point of tangency? Well, let's look at the blue line. Let's observe as I move the line. What's going on here? It looks like the line is going to touch my circle at only one place. And at the radius, which is at the center of the circle, it's going to form some angle, which some of you already know. So if I look at this bottom one, I have a line that is that tangent. I don't know. As I move it, what's going on? Well, it's not tangent because as I move the line, it's going to touch at some places at more than one place. So that line is not tangent. I want to show you one that is, one's not. But look at the angle. We're exploring the angle. That angle, when it looks like it's almost at 90, it looks perpendicular when it's almost at 90. So the question is, and I think we already answered it, what happens when a line is tangent to a circle? This angle formed, which I have hidden here, is 90 degrees. So to make a long story short, if a line is tangent to a circle at the point of tangency with the radius, it's always going to form a 90-degree angle. But that's only if they give to you and tell you that it's tangent. So let's do a proof that just talks about this. And this is a proof of a construction that's in your textbook. And if you wanted to follow this, it's on page 414 in your textbook. And it's a construction of a tangent to a circle through a point. So, all right. So we're going to start here with our proof. And it says two circles share center A, points. So we got small circle, big circle. Okay. Point C and E on the small circle. We got a small circle, point C and E, and points B and D on the larger circle. Okay. CD is perpendicular to AB. CD is this segment, is perpendicular to AB. Okay. Follow. If you follow and understand a proof, every step is logical. It's like you're establishing truth. Everyone knows that A squared plus B squared is equal to C squared. Why? Because it works every time. The quadratic formula works every time. There's certain statements that are just true, and we can prove them mathematically using a proof. So that's what this is, logical statements to show something true, true statements. So this is very important. So follow. Anyway, all right. So we're trying to prove that BE is tangent to circle A at point E. That's what we're trying to prove. So, let's go through our statements. All right, the first one says point C and E are on circle A. That's nothing exciting. They gave me that. Okay, so that's a given. Okay, number two, we have points AC, segment AC is congruent to segment AE. Well, I want to mark this up, so I'm going to move to another board. And what I've done, what we're really going to be doing, we're going to be proving triangles congruent. So notice I have this red triangle up top. That represents this top triangle that I have drawn down here. Okay. This one over here on the right, that's going to be the bottom right triangle here that I have this in blue. These were overlapping and I couldn't make them blue. So, but they're really blue because they're really in both triangles. Okay. They're actually blue and red in those spots, if that makes sense. All right. So here it says AC is congruent to AE. I want to mark that. So AC is this segment is congruent to AE. So AC congruent to AE. All right. Why can I say that? Because they're both radii. The radius of a circle, so I know they're going to be congruent. Okay. Next, it says point B and D are on circle A. That was given. Nothing to think about. Next, it says AB is congruent to AD. Well, AB is this whole top line. But notice it overlaps a little bit here. But I have it up here. Is congruent to, lost my, AB is congruent to AD, which is this entire segment, which overlaps the other triangle as well. So that's going to be here. Okay, very important. All right. Next says angle A is congruent to angle A. Well, that's the same. Notice this angle is in both triangles. That's why we have to say angle A is congruent to angle A, because it's the same angle. That's why it's the reflective property. So this is here, and this is, I'm marking the wrong place. I should mark it here, and I mark it here. Actually, let's go back and get rid of that one down here. So we mark it here, and we mark it here. So far, so good. All right. It says, so notice this triangle over here and this triangle. If you remember your triangle congruence theorems, I have two sides and an included angle. Two sides and an included angle. That tells me that these triangles are congruent to each other. So if two triangles are congruent to each other, I know that their corresponding parts are also congruent. That was really the whole point of doing this proof. So notice here, I have triangle AEB. The top triangle is congruent to triangle ACD. Cool. So next says CD is perpendicular AB. That was given. That was in our original statement, that CD is perpendicular to AB. Okay, that's very, very, very important. Let's keep going. The measured angle ACD. ACD is 90. And I need to do this because I'm using the definition of perpendicular angles to prove that the lines are going to be tangent. So that's important. So if they're perpendicular, you know it's equal to 90 degrees. So the measure of angle ACD is equal to 90 degrees. Okay? So I know that number 9 says the measure of angle ACD is congruent to, and let's look at this triangle up here. ACD is congruent to triangle angle AEB. Why is that? Because those are corresponding parts of congruent triangles are congruent. So I did all that to show that, well, almost there. Let me not mark it yet. So I know since they're congruent because of CP/CTC, I know that their measures are going to be congruent. So number 10 says their measures are congruent because of the definition of congruence. And number 11 says that measure of angle AEB is 90. Well, I know if they're congruent, if one's equal to 90, the other one's equal to 90. So we're just doing substitution. And number 12 says that AE is perpendicular to BE. Beautiful. So I know that AE is perpendicular to BE. Well, if you remember, that's what I was trying to prove from the beginning. If y'all remember? So here, and I'm going to go back up here and show you, I was trying to prove that BE is tangent to circle A at E. That's what I was trying to prove. So here it says BE is tangent to circle A. And why is that? And that's because of the converse of a theorem that says if a line is perpendicular to a circle at the radius, then it's tangent to the circle. And the converse of that, or basically the opposite of that, is true, which we proved that we have the line that's perpendicular to the circle. Therefore, that line, which is line BE, is tangent. So hopefully this helps. And in your problem that's in your actual 10-2, the Math Excel, it looks like this for the construction. And just notice if I move this anywhere, they may have your picture that looks like this, or they may have it like this. But basically, I want you to focus in and look for the two triangles. So this is, again, this is just a construction of proving that proving that this segment BE is in fact tangent to this little small circle AE. So hopefully that helped. All right, thanks.